Welcome to the second part of catalytic organometallics. Subject of today are the basics of transition metal catalysis. And we will start with the electron configuration of, generally catalytically active complexes. In the main group chemistry, we have the 8-electron rule, which means we have the electron configuration of, we try to adopt the electron configuration of inert noble gas. And similarly, in transition metal catalysis, we have the 18-electron rule. So, let's start with an example. Palladium in the oxidation state 0. Well, palladium is the element number 46, and as the electron configuration, we have the electron configuration of krypton, and additionally fully occupied d orbitals and 4 d orbitals and empty 5s orbital and the 3 5p orbitals also empty. To get to the electron configuration of xenon, we of course need 2 electrons for filling up the 5s orbital and another 6 electrons for filling up the 3p orbitals. Well, then we have the electron configuration of xenon, and this must not necessarily be very stable, but it is clearly saturated. Well, okay, so for palladium, this means for palladium 0, this means, there is a rather common complex with phosphines, triphenylphosphines, with 4 equivalents of triphenylphosphine, we get tetrakis triphenylphosphine palladium, which is regarded as a very useful catalyst in palladium catalyzed reactions. Well, although it is a saturated complex, coordinatively saturated, so how do we have to count to notice that this is coordinatively saturated? Well, let's start with a table. A ligand, a phosphine ligand, are 3 substituents, has the charge of 0, but with a free electron pair at the phosphine, we have 2 donor electrons, which are donated to the formation of the complex. So, oxidation state 0, 4 phosphine units makes overall 8 electrons. That means this complex has then the configuration, electron configuration of xenon is coordinatively saturated, and since this is then saturated, well, it can't interact, for instance, with olefins because it is saturated. Therefore, this means this is certainly not the catalytically active species. Well, but no problem. There are, of course, equilibriums in solution with the palladium with only 3 phosphine ligands, a 16 electron complex, and the one with just only 2 phosphine ligands, a 14 electron complex, which is indeed regarded as the active catalytic species, for instance, in the famous Heck reaction. So let's have a look at other ligands. An olefin, where the metal is coordinated to the central electron density, this would be called as an eta 2 alkene complex. You can also call it dihapto. It's another word for it, dihapto complex. The charge again is 0, and it also delivers 2 electrons. The same is, of course, true for the similar alkyne complex, eta 2 alkyne. And now compare it with a complex like this. Here we have an ethanol substituent or a vinyl substituent or even alkyl or aryl metal. Well, in all these cases, the ligand, well, is regarded to have the charge -1, and it delivers 2 electrons. Other interesting examples, well, just to add, of course, the same is true for halides like chloride, bromide, iodide, or other substituent acetate, for instance. Yeah. Also -1 and delivering 2 donor electrons. Let's go on with this table. What about this one here? A cyclopentadienyl ligand. This is eta 5 cyclopentadienyl. The charge -1, and it delivers overall 6 electrons. we also know complexes where an aryl ring, benzoic aryl ring is coordinated by a metal, for instance, chromium complexes we got to know in stoichiometric organometallics. In this case, well, we have a charge of 0 and again 6 electrons. Another interesting case is one of allyl complexes. This here is the eta 3 allyl complex, charge -1, and overall 4 electrons. Well, I should add that this is the general scheme for an eta 6 aryl complex. Well, let's have a look at this complex, bis triphenylphosphine, palladium, dichloride. While the tetrakis palladium, the tetrakis triphenylphosphine palladium complex has a tetrahedral coordination sphere. In this case, it is square planar. We have an oxidation state of +2, since we have the 2 - 1 chloride substituents. Well, since this is a palladium-2 complex, and with a palladium-0 complex, we need 8 electrons to get the noble gas configuration. With palladium-2, we need 2 electrons more. That means we are in need of 10 electrons. Well, we have overall 4 substituents, all delivering 2 donor electrons, and that means overall this is a 16 electron complex, 16, which is coordinatively unsaturated. And that means that, for instance, this palladium complex could coordinate to an olefin, for instance. By that, then a reaction could start. Okay? It could be already catalytically active. Another nice example. Such an intermediary complex we will discuss later on, maybe already next week. And this intermediary complex has been trapped and stabilized by a phenanthroline ligand in the presence of phenanthroline, this can be isolated. This has been done by Professor Alan Canty from the University of Tasmania in Hobart. And he did a nice experiment with that. Well, let's see. What kind of complex is that? It's also a 16 electron complex, coordinatively unsaturated. You see, -1, -1. That means this has the oxidation state of +2, the palladium. So, since we have 4 ligands delivering 2 electrons each, this is then a 16 electron complex. Coordinatively unsaturated, that means it can undergo an additional reaction, and it reacts indeed with, for instance, methyl iodide. And it adds methyl iodide and this complex is also, well, under moderate conditions, to be isolated. So what kind of complex do we have here? Now we have 4 substituents which are regarded as charged -1. That means this is a palladium 4 complex. Starting from palladium 0 is in need of 4 electrons. Palladium 0 is in need of 8 electrons. Palladium 4 in need of 12 electrons. We now have 6 substituents, all with 2 donor electrons. That means 12. Well, fine. This is then coordinatively saturated. Okay? That's how you can count that quite easily. So let's go on with key steps of transition metal catalysis. First of all, there is, of course, the ligand exchange. So, one transition metal plus a ligand, with a ligand there, and a ligand prime, another ligand is offered, and overall in some kind of equilibrium, we will get to the other situation, to the situation with the exchanged ligands. So, there are some similarities to, well, for instance, nucleophilic substitution, we know from general carbon chemistry. However, there are much more mechanistic options when working with transition metals. For instance, let's assume we have a coordinatively unsaturated complex of this general scheme. So, square planar, then here we have a trans ligand, this one cis, and this one also cis. A nucleophilic other ligand to be exchanged, this should be exchanged by that Y ligand. So, should be nucleophilic. This is coordinatively unsaturated, and then it just adds in. So, from a geometry which is square planar, we will get to a situation of a square pyramidal geometry. Now just a little change. The X ligand moves down to a position where it is located trans to the Y ligand. And this ligand just moves a little bit to this position. So then the geometry has changed to bipyramidal. Well, now you can imagine that again a change could take place, that this substituence moves into the plane of those three L ligands. Okay, then we are again in a square pyramidal geometry. And finally, X leaves a complex. And it's clear that we will have then the situation, the initial situation, but with X exchanged with Y. So, you see that these ligand exchange reactions or substitution reactions, some kind of substitution reactions, could proceed much more complicated as compared to what we are used to in chemistry of substitution at carbon centers. Well, and you can imagine that those ligands, of course, have a significant influence on the reaction rate, especially the trans ligand is the one who is determining the reaction rate, and by applying the right ligand, you can indeed trigger the reaction rate of such processes. So, in the case of a ligand exchange with a coordinatively saturated complex, for instance with this tetrahedral nickel tetracarbonyl complex, well, before you can exchange something, the one carbon monoxide has to leave the complex, and this is generally the slow reaction step. Then you have a coordination site where another ligand can coordinate. And well, that second step is generally the fast reaction step. Alternatively, with certain ligands present, coordination sites can be opened by a reaction you sometimes call a slippage, for instance, a ring slippage. Well, let's imagine we have an allyl, an eta-3 allyl complex. As we said already here in that table, we have a charge of -1 for the ligand and 4 donor electrons. And here we can sometimes observe an equilibrium with the eta-1 allyl complex. So again, still -1, but clearly only 2 donor electrons. Imagine that this one is with other ligands coordinatively saturated, as maybe an 18 electron complex. Then you have here the situation of an unsaturated 16 electron complex. Or cyclopentadienyl, -1, 6 electrons. From eta-5 cyclopentadienyl complex to an eta-3 cyclopentadienyl complex, -1, 4 electrons. This is the so-called ring slippage. Of course, thermodynamically disfavored, since it loses its aromaticity through this step. Well, but nevertheless, it can go on in equilibrium to the eta-1 complex. So here, eta-5, eta-3, eta-1. And here we have, again, -1 and 2 electrons. Another example, not a cyclopentadienyl complex, but just a pentadienyl complex. of a manganese carbonyl. So, here manganese has the oxidation state +1. It's a D6 complex, 18 electrons saturated. There's an equilibrium possible from eta 5 to eta 3. And now it is an unsaturated, coordinatively unsaturated manganese complex. If another ligand is offered, it can coordinate to the manganese. So, and if now in equilibrium a carbon monoxide leaves the complex, then it can return to the eta 5 situation now with only 2 carbon monoxide ligands, but in addition with the ligand which has been introduced by that ligand exchange. So after ligand exchange reactions, let's discuss reactions which are called oxidative addition and its reverse reaction, a retro reaction, reductive elimination. Generally scheme, a metal in the oxidation state N reacts with a molecule AB and the oxidative addition will lead to a complex with A and B as ligands or substituents at the metal, and the metal has changed to the oxidation state N+2. So, and the retro reaction is the other way around, and it's called reductive elimination. So, generally, rather electron-rich transition metal complexes, those, for instance, with phosphine ligands, react quite nicely with carbon halide bonds under oxidative addition reaction. If you have carbon monoxide or cyanide as ligands, then this diminishes the electron density and hinders oxidative addition reactions of that kind. On the other hand, electron deficient complexes might react with more electron-rich single bonds. Well, for instance, carbon-hydrogen bonds. Well, let's have a look for some examples and the mechanisms which can occur for oxidative addition reactions. For instance, the SN2 type oxidative addition. Let's assume such a square planar complex with methyl iodide. And it should be a slow reaction step, just adding the methyl iodide via a nucleophilic substitution SN2 type process. So, and the fast reaction step should be the next one, where the iodide then also coordinates to the metal. Well, actually, we already have discussed an example for that. Well, it is the oxidative addition from a Palladium 2 complex to a Palladium 4 complex, as reported by Alan Canty. So this is SN2 type. Another type of oxidative addition, once again with a general scheme. So these brackets here symbolize that there is, of course, not a naked metal. There are already ligands and substituents. So it reacts with the reagent AB, and in equilibrium, that unsaturated complex might coordinate to the electron density of the single bond between A and B. This is called an acoustic interaction. And it often leads then via a 2-electron 3 center bonded system to the oxidative addition product. This one. One example which has been studied in detail is a tungsten complex. So what kind of geometry does this drawing symbolize? Well, those four substituents or ligands are in a plane, and with this one it is square pyramidal. If molecular hydrogen is offered, then that molecular hydrogen can be coordinated to the tungsten and indeed this dihydrogen complex, was isolated at low temperatures and was analyzed by X-ray diffraction, and it was found that we have a bond length between those two hydrogen atoms of 0.82 angstroms compared to 0.74 for the molecular hydrogen. There is a further equilibrium to the complex where the hydrogens are clearly separated. Well, I didn't find the distance for that case. However, this is then not a dihydrogen complex anymore, but a dihydride complex. And it should be clear for everyone that these equilibriums are important for hydrogenation reactions under homogeneous catalytic conditions. Similarly, the oxidative addition of Palladium 0 to carbon halide bonds where the carbon is sp2 hybridized. In these cases, we cannot assume some SN2 kind process. As you know, we don't have SN2 reactions also in the normal carbon chemistry when a carbon is sp2 hybridized. There we have always addition elimination processes. So Palladium 0 with these 4 ligands could be 4 phosphine ligands. As already discussed earlier, there is then the equilibrium until the 14 electron complex L2 palladium, which is regarded to be the one that is catalytically active for the oxidative addition step. So, an aryl halide, then it is assumed And also in this case, we have three-centered system. And finally, from Palladium 0, we have changed, well, Palladium, a 14 electron Palladium 0 complex to a Palladium 2 complex, still coordinatively unsaturated, since this is a 16 electron complex. So these will be important as intermediates when we will discuss the Heck reaction in the next lecture. Other mechanisms which might occur for oxidative addition processes are ionic pathways, for instance in cases where you have cationic transition metal complexes, which are very often highly reactive because they are so electron deficient. And one should keep in mind that also radical reaction pathways can occur and have been indeed proven for some cases. So, next subject are insertion reactions. For instance, insertion of carbon monoxide. So, carbon monoxide is offered to a coordinatively unsaturated complex with a substituent R, maybe an alkyl or aryl substituent. It will coordinate to the metal. And then, in equilibrium, it could insert into the carbon metal bond, forming such an acyl complex. And indeed, this reaction, it is an equilibrium since it is reversible. Similarly, the insertion of an olefin, and that's almost the same as the insertion of an alkyne. So, an olefin plus, again, such a complex with a substituent R. You see the mechanism is in principle all the same. The olefin is coordinated at the metal, and the insertion reaction takes place so in this case, that insertion reaction we would call a carbometallation if R is indeed a carbon-centered substituent. and this is also a reversible process. Well, if R just is a hydride, then it's a hydrometallation, and this, as you know, is also reversible process, as you have learned for the hydroboration. And this type of process, well, generally is a concerted one which proceeds in a Zön fashion. Let's assume we have hydrogens at the beta position. So then for a beta hydride elimination, this carbon-carbon bond should rotate until a hydrogen is in a Zön periplanar position. And then a concerted beta hydrogen elimination, beta hydride elimination, can occur. The first step with the metal still coordinated to that olefin, while the readdition could occur, and so on. This is also a typical process which we will, well, discuss again the next session with the Heck reaction, of course. So, what remains to be mentioned, that is the transmetallation. Of course, you already know the transmetallation as a typical step of in stoichiometric organometallics. So, we have some organometallic compound and a transition metal complex with a substituent X, most of the time a halide. And this would be then the transmetallation, where M prime in brackets symbolizes a transition metal complex or complexated transition metal, and M, well, can be lithium, magnesium, zinc, boron, tin, zirconium, silicon, and some more. So, with this overview, we have discussed today We have all the instruments we need for discussing transition metal catalyzed reactions in details, and as I said, we will start then with a hack reaction on next Tuesday. Thank you for listening. See you next week.